We'll wait another 2-3 minutes before starting. Since today is the first session, people might have trouble joining. You can hold on to your questions. They'll be answered in the first couple of slides. I just want to start after people join, because otherwise I'll have to answer the same questions 10 times. So you can ask them, but I will cover them through the slides. And if you still don't get an answer, feel free to ask again. We'll start in a minute more since people are joining. Okay, let's get started. Good evening and welcome to the week 1 live session of the CS104 course. And hope you can see my screen and hear me clearly. If not, at any point during the call, if you find internet issues or you're unable to hear me, please respond on chat. Great, you're able to hear me. So before we get into the course, so here's how we'll handle today's session, right? We'll handle some of the logistics and some of the questions that most of you would have about how these live sessions work and what can you expect out of them and things like that. And then we'll move on to the week 1's content. Okay, let's get started. I hope most people have joined. Right, so the first question that all of you have been asking me, is this the first session? Was there another session? So for this course, there are 2 live sessions conducted every week. Okay, people are still joining. Let me just wait for a few more seconds and then continue, because I'm sure all of you have these questions. Okay, let's continue. So we have 2 live sessions every week at 2 different times. Since many people, including students, working professionals, faculty, register for an NPTEL course, typically we have multiple live sessions offered for each course so that you can attend based on your convenience and your schedule. So you don't mandatorily need to attend both. Both of them will have similar content. They may not be exactly the same, but they will be very, very similar. So you can pick whichever one works for you in terms of timing, or whichever one you feel is more interesting. That's up to you. In case you still want to see what happened in the other live session, there will be recordings and slides posted after the session. So you will be getting access to a sheet in which you will have the slides link as well as the recording link for both the live sessions. So some of you said you missed yesterday's session, you want to listen to whatever happened there. So that sheet should reach you sometime this week. So then you will be able to see the recording and the slides. And the same goes for today's session. So don't worry in case you miss some part of it, or you can always replay it and look back at the slides. So I will be handling the sessions that happen every Monday at 7 to 9, and a different team member will be handling the ones that happen Sunday 6 to 8 p.m. Okay, people are still joining. This usually happens in the first session, but please try to be on time from the next week onwards. I understand you can have difficulties finding the link or getting things to work the first time, so that's okay for today. So what do you kind of expect from a live session? These are mainly intended to help you understand the concepts better, and then help you solve the assignments. Let me take a look at the question. Is there an IIT WhatsApp group? I'm not really sure. So NPTEL as such officially gives you a Google group for discussion. In case you haven't already seen that, you can go to ask a question on the course, and that will take you to the Google group. So there you can ask questions, you will receive answers to those questions and so on. It's meant to be like a discussion forum. I am not aware of any official WhatsApp group. If some of you have created something unofficially, then that's up to you. That's the answer to that. So going back, what do you expect from these live sessions? So these will be focused on problem solving, and they are kind of intended to help you with your assignments. So for instance, and this will always be aligned to the week X. What I mean by this is, today is week 1 live session. We will be covering topics from week 1 of the course, right? And it's always going to be like that. There are going to be 12 live sessions for this course, and each live session will focus on that week's content, right? And this is also intended to be interactive. So if you have any doubts with the course content, with something that you didn't understand, because these are all pre-recorded lectures with no interaction, feel free to ask those during this session. In fact, I encourage you to ask it, because this is the easy way for you to get those things clarified. And since we have more than, so we have almost 36, 37 people here today, so we will use the chat box exclusively, because people unmuting and talking together at the same time kind of is difficult to manage and coordinate for a larger audience. So whenever you have questions, you can post them in the chat box. I'll either reply to it immediately, or if I'm in the middle of something, I might take 5 minutes to come to your question. But that's basically how we will have questions and answers. Apart from that, like I said, after the session you will get access to the slides and the recording. The recording will be in YouTube, and the slides will be on a drive folder, and this will be shared to you, okay, via mail. So however you've been getting the course announcements, right? For instance, an email saying that there is a live session today. Similarly, you will get some form of notification saying that here is the file with all the links to the recordings and the slides, and you can use that to find out any live sessions, recordings and slides, right? So here's the overall logistics. Any further questions, something that I didn't answer, please ask. Link for demo software, that would be shared through the course itself. If that is not, you can ask it on the discussion forum, and there are other team members who are in charge of doing that, and they might reply there sharing links for you. But this is not intended to be a hands-on kind of a session, so we can go through some difficulties that you have if needed. If you, for instance, tell me this week that you are having trouble installing some particular thing, I can look it up, but that's outside the scope of these sessions. So the preferred method is to talk to people, ask on the discussion forum. So week 1 slides again, Week 1 slides, there is a link, but that doesn't seem to be working. That should be fixed soon. I think a bunch of people have asked on the Google group too, so don't worry about that. It should be fixed in a few days. Hopefully by next week it should be fixed. So after that you will be able to download the slides. Okay, assignment questions are not all video based. Yes, they may not be, and that's something we will discuss today on what are references for a course like this, right? What do you need to study? What, from where can you kind of understand more than what the videos cover? But most of the questions will be based on the class videos. Not all, but most. Resume inputs. Okay, that's completely outside the scope of these sessions. Let's see, maybe at the end, if we have time. People are still joining. Okay, if we have time at the end of today's session, we will look at that, but that's completely outside the scope of this. So for now, let's skip that. Okay, so for people who just joined, here's a quick recap of the logistics. There are 2 per week and you only need to attend 1. In case you want to watch the other, it will be available on YouTube. You will have access to the slides too, and we will use the chat box for all interactions. Now let's go through a little more details on the live sessions. So how I have these live sessions is we will have a quick recap of that week's course content. This is mainly for you to clarify your doubts or your questions and things like that, and it is not okay, we have a question. Yeah, like I said here, it will be similar content. It might be slightly different based on, for instance, I might choose to highlight some topic more because many of you did not understand that better, or you're asking me questions about that, right? So the point of a live session is that it is interactive, and because of that there will always be some difference between 2 live sessions conducted on the exact same topic. But beyond that there is no difference, so you can always attend one. If you want to attend both, that's completely up to you. Yeah, going back. So I prefer to have 3 parts to these sessions. First is a recap. I won't do an entire recap of the 2 hours or 3 hours worth of videos because that's kind of repetitive. I will pick out a few slides and I'll go through them. And if you have any questions, either in those slides or something else that was covered in that week, feel free to ask. Then we will have approximately 1 hour problem solving. And why I say approximate, this depends on that week's course content, right? For instance, in some weeks you might have numerical based questions which take longer to discuss and solve. So that might take the full 1 hour. Or in some weeks you might have things that are just recalls or definitions and things like that. That might take 30 to 45 minutes. So accordingly this 1 hour might either stretch or it might go down. And then finally we will have a dedicated time for doubts and questions towards the end also. And we'll go through any other questions that are there on this discussion forum. And since this is a 2 hour class, we can have a short 5-minute break so that people get a chance to get some water or coffee or whatever you want. So we will typically do that around 8 and come back at 8:05. You can stay on the call, just leave it muted. That's what I do. So this is broadly the structure of the live session, but I'm open to feedback on that. If you feel you don't understand the topics, you want to have a more detailed recap, we can work on that, we can do that. Or if you feel, no, those topics are quite clear for me, I want more help on problem solving, that's also fine, right? So we can figure that out as we go. If at the end of today's session, for instance, if you have any inputs on this would be better, please share that on chat, right? I'll take that into consideration for the next week. Although today I think we'll be spending around 20-25 minutes just going through the live sessions and how they work. And again, interaction is the primary goal of these sessions, so don't ever hesitate to ask a question. It's fine even if you feel this is not so important, or this is very silly or very small to ask. Feel free to ask, right? That's okay. And even when I explain the answer to a certain question, if you don't understand that explanation, feel free to ask. and sometimes I might not be able to give you an on the spot answer, but I will definitely get back to you in the next week's session with a concrete example so that you can understand it better, right? So that's about the logistic. Let's look at the questions we've gotten. Where do we get a sample question paper? That I haven't seen in any of the courses so far, but the intention of these live sessions and the assignments that you are given is to kind of help you build up to that sample question paper, right? So by solving these questions, you will be able to solve any question that turns up in a sample question paper. Apart from this, I don't think NPTEL releases a sample question paper as such. This online based AI certificate will give you a salary hike in your job. Hopefully, that's one of the reason people join this course, and hopefully it will. So try your best to gain all the value you can from this course. Okay, so with that, yeah, so what should you do to kind of benefit from this live session? There's again a few things that I'll talk about. So watch that week's lectures on NPTEL before you come to this session. So I think the lectures are released on Sunday or Monday, something like that, right? So week 2's content is already live. All I'm asking you to do is to watch the previous week's lectures in this 1 week that you get. So for instance, you would have had, if week 1's lectures were released last Sunday, you would have had a whole week to kind of catch up on that. Please do that before you come to this session, because only then can you ask doubts, right? And you will know how well you understand that session, what are the parts that are not clear and things like that. So to make full use of this session, the first thing you should do is watch that week's lectures. The second part is try to solve the assignment. Again, this will give you an idea of what questions are difficult to solve or what you don't understand well, and then we can use these sessions to focus on that, right? The third part is not really mandatory to get the best of these sessions, but I would definitely recommend it, especially if you're trying to go beyond what is just covered in the course and what is just covered in the assignments, right? So this is, if you've noticed in the slides, there are references or links given in many slides, right? So follow those references and try and read what they have, right? You need not read the whole thing. Again, we'll talk about this a bit more. I think there was a question at the beginning also saying what are the references for this course. So I have a slide on that, so we'll go through that in a little more detail, but at least look through these and see if you understand something at a very high level. What is that link telling you, right? And you can ask questions from there as well. So I might not have and those questions are slightly out of scope of these assignments or problems, but that's still okay. We can I can answer those either on the spot or in the next week, right? This will really help you understand a lot more beyond what is there in the videos. So I strongly recommend that, especially if you're doing this as a postgraduate level, so you can do that. So let's look at the questions. Question of week 1 content in week 2. We can entertain a few of those questions, but majorly the idea is to cover 1 week's questions in one session, because there are 12. Now suppose I take 2 or 3 live sessions just to cover week 1's doubts and questions, then the remaining 9 I'll have to squeeze in the rest of 11 weeks, right? That's not very ideal. That doesn't mean that if you get a question at a later point in the course, you shouldn't ask it. That's not what I'm saying. What I'm saying is try your best to watch the lectures before you come in and ask whatever questions you have at that point. If at a later point in time you have a question from a previous week, that's always welcome, right? But don't use this to kind of postpone everything to the last 2 live sessions and watch all the videos and ask me 100 questions then, because that is not going to help either of us. I won't have the time to take up all those questions, and you won't benefit from all of them thrown at you in one shot. So be methodical about it as much as possible, and if you have some spillover questions, we can take that in a later session. What is the type of final exam? It is typically MCQ. It is not subjective. and that's the format of all NPTEL questions, I think. So it should be that way. If you've gotten an email on the exam format or something like that, please check that as well. This is not from some knowledge I have of seeing the exam or the question paper. This is just based on my teaching multiple NPTEL courses. So far all the courses I have taught have not had a subjective exam. So please double check that. I'm not too sure, but it's mostly an MCQ. Okay, will we get to know the marks for the assignment after each deadline? Yes, NPTEL typically releases an answer key where they tell you that this option C is the answer for this question and so on, and that way you will get to know which of your answers are right and which are wrong. Again, if you have doubts in that answer key that is provided to you, if you for instance don't understand why the option C is the correct one, feel free to bring it up in the next live session, right? And we can always go through that. Okay, were there any other questions? Okay, directions about projects you can take along with this course. Can I expect some mentorship on a personal project? Again, I think this is out of scope from an NPTEL perspective, but as a general opinion, I think you can take projects that involve some intersectionality of systems and machine learning, right? This course by definition is an interdisciplinary course. It is not purely about machine learning or AI. It is about how you kind of deploy AI, or how you kind of productionize AI in a very performant way, right? So you could take up projects that look more into detail on that, but again, I'm not aware of what exactly you're asking here, right? Because I don't know if you're an undergrad student or a master's student or a PhD student. So without all of that context, I can't really figure out what would be the best choice for you. And again, like I said, it's out of scope for these live sessions. And personal mentorship also from an NPTEL perspective is not really part of the duties of a TA, right? So that's that. But if you have any particular questions, like I said, after the live session, you can kind of ask it, and then we'll figure out if that's doable at all. But in these 2 hours, I think with the limited time we have, I don't think we can get into some of that. Previous year's questions for the course. So that's some of the material that I will be presenting to you through today and the later live sessions. The assignment questions that I am picking are from previous year's questions. So this course was run last year as well. So that's what we will be using for those. So those are already covered in the live sessions. You don't need to worry about getting that separately. Okay, difference between V100 and A100, which is most prevalent? I think we have a short difference coming up later in the slides. If that doesn't answer all of your questions, then we can have a more detailed discussion in the next session, right? But yeah, I'll note down your question, and I will make sure to get back to it. Just give me a moment while I copy it. Yeah, that's good. Okay, so great. Yeah, we will because we will get into your question in a couple of minutes. Before that, I want to let's see what I have. Yeah, I think most people have joined now, so I want to do a quick introduction so that I can get an idea of the audience. Again, this is not so that I want to know which colleges you're from or some information gathering thing, right? I would just want this so that I can tailor the session accordingly. For instance, if most of you are from an undergraduate level, many of the concepts that are presented here might not be clear to you, right? So from that perspective, I would like to know a little bit about all of you guys. So here's a template that I would suggest: your name and what do you do, right? This could be like master student in this college and whatever branch you're in. And if you're a working professional, you can say ML engineer in so and so company or whatever. and what do you expect to learn from this course, right? Just take a couple of minutes to put this on chat. For instance, I will introduce myself as Prashanti. I'm a PhD student at the Indian Institute of Science, and I work at the intersection of systems and machine learning. So go for that if it would help me understand where you're at, right? Because like I said, there is a lot of difference in what you would know if you're an undergrad student versus what you would know if you're a postgrad student. Okay, hi Likita. Theoretical approach of AI. Okay. Please put your name and your introduction in the same line, like one full message. That would be helpful. BTech. Okay. Okay. Nice to meet you, Varsha. Okay, BTech. MCA, very interesting. Don't hesitate too much about this. It will also help you know your batchmates better, right? BTech third year, hardware accelerator, very nice. Hi Amit, nice to meet you. Hi Aditya, nice, better understanding of DLML. AI/ML applications in healthcare, interesting. Practical knowledge into TensorFlow, okay. Model compression and deployment, okay. BSc second year, nice. MCA, good understanding of AI/ML, okay. Majored in math, learn and understand AI. Okay, great. Nice, very nice to meet you, Atar. TinyML, interesting. Practical knowledge in AI, biomedical engineering. PhD, nice. Okay. Accelerated programming, Kubernetes, okay. Botany, nice. Okay. Very interesting set of expectations from the course. And we have a fairly diverse cohort. So okay, we'll wait a minute more in case any of you have not gotten a chance to write a quick intro so far. So, but I noticed a bunch of people joining in. Hi Kunal, great, nice to have you. More light on TC, okay. MSc first year, nice. I'll just stay on this slide for people who joined in the past 5 minutes. this broadly covers the logistics of the live session. You can go through it, and if you have further questions, feel free to ask on chat. Interest in AI, nice. Nice. Systems background is rarer than ML and AI these days. Great. Nice to know that you're so keen about AI. Hardware architecture. Okay. Yeah, we will get into some of that in this course. Thanks for sharing. Okay, anyone else? Okay, if not, we will move ahead to looking at what the course covers. So I asked what you expect to learn from this course to set expectations, right? It's important to know what you will gain from this course and what you won't before you start the course. So, okay, we have a few more introductions coming in. Hi, BSc Math, very interesting. An AI and DS course, along with this, what are the career perspectives? How will it help? So this course again is an applied AI, right? It's the perspective of how do you accelerate artificial intelligence? How do you get performance out of AI and ML, right? There might be other theoretical AI courses. For instance, I noticed a bunch of you saying that will this course help me understand theoretical AI, right? It won't really, because you're going to understand what neural networks are or what deep learning is at a very high level. But if you want to go into the theory of, let's say, backward propagation, that itself will take you an hour. So this is an interdisciplinary course that looks at the application of AI rather than AI itself. So taking an AI course that's more focused on the theory might help you build solid ML and AI fundamentals. Data structures course again could help from a programming and a coding perspective. And overall, if you're looking for an ML role, it would help. But yeah, that's a very general answer. Yeah, theoretical will plus applied if you're looking for an ML role specifically, where you're expected to know a lot more about the models or about the algorithms and design better models, design better algorithms, right? It will definitely help. If you are looking at a systems role that perhaps needs you to optimize existing AI models, existing algorithms, then this course would be mostly enough. Okay, let me look at other questions I had. Is this course too complex? Again, that depends on you and your background, right? So typically the way I would look at it is go through a week or 2 weeks worth of material, try to read up on things that you don't already know, and then try to calibrate where you're at, right? If 90 or 95% of the things seem way too difficult and you have no idea about what some of those things are, then it is probably too complex for you and you would benefit from a simpler course. But that being said, I'm not saying that an undergrad person cannot take this course or something like that, right? We will in fact go into some of those things. What I'm just saying is, for instance, if you look at week 1 and what was taught, we broadly looked at systems hardware, we looked at containers, and we looked particularly at GPUs and accelerators. Now, what you could do if you understood none of this is to pick up an OS primer or a quick revision sort of material and go through OS if you have not already learned that. Similarly, a brief background on computer architecture would help. But even after doing all this background reading, if you're unable to understand most of the course and you find that even the live sessions aren't helping you too much, then the course is probably too complex. But again, I would recommend giving it 2-3 weeks before you take that call, right? And again, this differs from person to person depending on what background you come from and what are your strong skills versus what you still need to pick up. You might need to make a different choice. Okay, a few more introductions. Will we be taking questions on what we learned so far in this session? In week 1, yes, we will be doing that. I think we're already at 40 minutes, so we will get into the actual content for this week so that we have some time for questions. And why does hypervisor have to be invisible? Again, we'll get into this a little bit later once we get to the actual topics that we were supposed to cover this week. Okay, research student have to design new models. How models are created in a deeper sense. Mostly from what I've been looking at here in terms of the syllabus, not really. For that you would need to have a deeper understanding of the architecture, right? So this you can kind of take it as an introduction to models and how architecture is and things like that. But if you really want to design newer models, you will probably have to take a more ML focused course. But this would be a good starting point to understand the space of models. For instance, we have a good bunch towards the end, we have a few applications, right? NLP, smart cities, bunch of things like that. Those will help you understand the breadth of the area, and then you can probably go deeper into things that we need to cover. Okay, let's see. Do we need to learn ML and DL? Hold that question, I'll get to it in a slide. What are the CSE prerequisites? Again, I'll get to that in one slide. Question from week 2. Today, I doubt we will have the time to go through it. So what you can do is drop your question in the chat box, and that way I will get back to you in the week 2's live session where it is supposed to be covered anyway, right? So you can do that, and I'll note down your question, Kunal. More on how to set up Docker. I haven't watched the videos yet, but hopefully there were some instructions on how to set up Docker in the videos itself. If not, I can share. Okay, you've already installed it. Okay, what do you have a particular question on the setup then? Practical assignments, again, I think so. Previous courses have had them, at least 1 or 2 practical assignments, but again, I'm not too sure on this. I can check and get back to you next week. Let me note that down too. Yeah. Okay, so you want to, okay, I'll make a note of your question, and then I will take a look at what the video talks about and what is mentioned, and then we can I can share a link or something. But like I said earlier, to show you a hands-on setup or something like that is out of scope of these live sessions. Okay, so this is what broadly the course looks like, right? So week 1 is intro to systems hardware, week 2 is intro to containers, and then you have Kubernetes and distributed computing. Week 4 and 5 are about deep learning and machine learning frameworks like PyTorch and TensorFlow. And then from week 6 we get into optimizing deep learning training, and one of the primary things that we can do is to do distributed training. So week 7 gets into that, and week 8 looks at accelerating inference, right? Training and inference are the 2 primary modes of deep learning. And finally we look at some application sort of stuff with data analytics, NLP, applied AI, and this year I'm told the course will also have a module on LLMs, right? So that's broadly the structure of the course. Now coming to references, prerequisites and things like that, right? I think a bunch of people had questions on that. So because this is an introductory, okay, let me just look at that comment. Program shows Linux based Docker use case which uses CLI. Windows has a desktop manager. Okay, great. So if you're able to figure out which one works better for you, you can always choose to use a desktop one, right? As long as you can figure out what you need to use from the GUI, that's your choice. Or maybe you have a Windows machine and you want the GUI version, that's up to you. Unless some assignment specifically asks you to use a Linux based CLI based version of Docker, you don't have to. That's primarily your choice. If you particularly want something and you're not able to do it, then ask me. A choice of GUI based versus command prompt is yours to take, depending on what you're familiar with or what OS you have and things like that. You can figure that out. Great. Moving back to this. So there are no textbooks as such, right? There is no one reference saying, for instance, if you take an OS course, you will be recommended the Galvin textbook or one of those standard textbooks. But because this is a very interdisciplinary course, if you look here, you might have seen a bunch of hardware related stuff, right? Broad themes, hardware related stuff, which includes things like OS, which includes things like accelerators, GPUs, FPGAs, ASICs, wafer scale compute. Then you see a bunch of stuff around frameworks, around system software, things like Kubernetes, containers, PyTorch, TensorFlow. And then you see a bunch of things that come from the deep learning or machine learning application space, right from models to training to inference and a bunch of applications. So this is a very interdisciplinary course because of that, and we can't possibly have 10 textbooks about each of these, right? Because you guys can't go through all of that. So instead, what is done is every week slides have references on individual topics. So these will be the primary references for that particular topic. So please go through them. Like I said before, it is optional, but it is highly recommended. That will help you really understand the contents of the slide much better, and it will help you go beyond that. And some of these references may be research papers. For instance, in week 1 there was one paper that had a bunch of accelerators and comparison along various terms, right? I hope some of you clicked on that link and opened it. If you did, it probably turned out to be a 15 or 20 page paper, right? So that might be intimidating if you're an undergrad student and you've never seen a paper before. But if you feel that I want to learn more about what this paper is saying, but I'm not able to do that, or I can't spend a whole week reading this paper, so how do I do it in an hour? We can have a quick 5-minute overview on how to do that, right? We can do that in the next week if you want. Where is the link? So the link will be on the slides itself. If you've seen the videos when they're playing, in the bottom of the screen you will notice some links being mentioned. For instance, in the wafer scale compute slide, you might have seen a blog from Cerebras talking about how that is different, right? So that's once you get the PDF of the slides. Right now you might have, I just realized you guys don't have access to slides yet, so you might have seen those links and not really opened them. But once you get the PDF versions of the slides, please do open them and try to learn more about whatever topics are covered. Need more discussion on Docker daemons? Sure, we can do that. In fact, I think today we'll run out of time. So one simple thing we can do is to take out all your questions. I will make a note of them and then I will kind of touch upon each of them in the next session. The other one is DJX1, define DJX1. So again, I think there was a slide talking a little bit about the architecture, so I'll go through that in detail probably in the next week. So in the next week we'll spend around 20 minutes talking about all of these questions, right? Because today I think we'll run out of time by the time we are just done with the recap and a few questions. Yeah, like I said, the slides will be released hopefully soon, so you will get a PDF of whatever is covered. Okay, how do we filter out what to learn? That's a very important question, right? It's a very interesting question because almost every single slide has a reference. So primarily ask yourself two questions, right? Either one or both. Is this something that's going to benefit me? If you're taking this course, you said all of you gave me a one-line definition for why you're taking this course, right? For instance, I want to learn more about hardware accelerators. Now, if there's a link about Cerebras and what is wafer scale compute, that is something you should definitely click on and read, because that is useful for you from whatever perspective, right? For instance, you want to do a project on that, or your work is about hardware accelerators, or you want to do a master's specializing in that, something like that. So that's one motive by which you can filter out what to learn. The second thing is purely how much time you have and how much interest you have in a certain topic. Again, this is driven by what level in your education or work you are in, but these are basically like a superset of all things, right? So different people might be taking this course for different reasons. So based on that and how much time you have, how much interest you have, for instance, some of you might be taking this course simply because your college requires you to take an NPTEL course and you need to finish some credits, right? You let's say you have 7 other courses with this and you don't really have the time to read extra stuff. So that's a perfectly fine reason, and it is a very practical one, right? So then you can be really selective about what you choose to learn. But if you have a good amount of time and you want to make the best out of this course, then you can try and open most, or if not all, of the links that are there in the slides, and then look at what is more accessible to you or what you understand. So for instance, technical blogs are very, very accessible because they are made keeping a variety of audience in mind. That blog post from Cerebras that I was mentioning is very, very accessible, right? Anybody can read it and go away with more or less a similar level of understanding. So things like that you should definitely read. Now the next level of complexity comes from things like research papers, which may or may not be what you're looking for, right? It will have a lot of fine-grained information that's very relevant for someone who's working exactly in that niche, but may not be super relevant for other people, right? That's another criteria you can use to filter and learn. But specifically, if you for instance have pointed questions on should I read this in detail, feel free to ask that too in the next class, right? We can kind of go over how important something is from your perspective or from a variety of people's perspectives. Okay, I think I've finished everything on the chat. Okay, like I said, some of these might be papers, we can go over that. If you feel this would be useful, please ask on chat. And again, if you feel something is not clear, so I noticed that the majority of you were undergrad students, and depending on which domain you're from, maybe like someone said, you're how to go through research papers quickly, I can do a 5-minute walkthrough of that in the next session. I will do that since one of you have asked, and we'll maybe do it towards the end of the session because I don't know how many other people are interested in this, but we can do that. Going back to what I was saying, research paper as a PDF. So the links that are shared with you are typically archive links which do not require some form of subscription, right? If ACM or IEEE links are shared with you, please ask me, I can share PDFs with you. That's not an issue, but most links that are shared on the slides would be archive links, primarily because again it's accessible by everyone, right? So please check for that, and if you're still not able to access some particular paper, you can let me know. Okay, a bunch of people are interested in how to go through research papers, so we can do that in the next class. I will note that down. Yeah, finally, if you need additional material, so this is what I was getting to. Since a bunch of you are undergraduate students, you might not understand some of these topics very easily. For instance, in this week's content, there was a lot about GPUs without actually going into detail into GPU architecture. So some of you might not have understood certain things about why is this like this, or let's say we are talking about tensor cores, you might not even have understood why tensor cores are the way they are, right? So things like that is a good thing to ask during these live sessions, and I can always give you additional material that is more accessible, that can help you understand these concepts better. You can always look on the internet by yourself as well, But if you feel that you haven't found something or you want a better resource to learn this from, you can ask me. The course might not go into detail, right? Because if the course starts talking about OS itself will be a week or two, and there is no time to cover every single thing like that. So some concepts might be dealt with in a very brief manner. So if you need additional resources, you can feel free to ask. Okay, why is there no L3 cache in the GPU? Interesting question. We can again think about that, and some of these questions I will also ask you to kind of make you think about why certain things are a certain way in the architectural level, and then we can come back and discuss it in the next week, right? That gives an opportunity for everyone else to also go back and think about these questions. So these questions are not just for me, for all of you guys here. Look at what your peers are asking and see if you can answer them, and if you can't, that's perfectly fine, but go take a look afterwards to see if you can figure out why or why not. Okay, so I think that's all I had about the logistics, the administrative stuff. Any final questions before we move on to this week's content? Okay, if not, let's move into week 1. So broadly we looked at 3 things, right? We looked at introduction to AI systems hardware. So before that we went into what is deep learning, what is machine learning. We looked at some traditional computing systems. What does a system typically have? How basically compute, memory and storage are tied together. Then we looked at modern memory hierarchy, we looked at data access versus computation. Then we looked at some specialized computation engines like GPUs and FPGAs. Finally, the second module was around AI accelerators, and again we looked at a bunch of different accelerators, right, from GPUs, and even in GPUs. You're not able to see my screen. Is that for everyone? I am sharing my screen. In fact, I've been sharing it from 54 minutes. So, okay, others are able to see. That's good. Yogesh, could you please drop off and rejoin and see if that fixes it for you? Great. So I will always be sharing my screen, just an FYI. So in case you cannot see it at any point in the 2-hour session, please drop off and rejoin and make sure you can see it, right? And if all of you can't see it, please let me know. Okay, so we coming back to AI accelerators. We have a bunch of different AI accelerators, and we have different even in terms of a GPU, we looked at things like edge GPUs and data center GPUs, right? And then we looked at some task and data parallelism. We looked at task versus data parallelism. We looked at visible now. Great, thanks. For anyone else who cannot see my screen too, please drop off and rejoin. Sometimes there are issues with the meeting software. But you should be seeing my screen because you don't have a reference for anything I'm talking about otherwise. Anyway, and if you missed out on some part, that's okay. You'll get access to the slides and the recording, which has a screen share view. So that should be fine. Okay, and then we looked at a comparison of GPUs versus CPUs. And finally, moving on to the third module, we looked at operating systems. We looked at why do we need an operating system, what are interfaces between the hardware and software, and then we moved on to virtualization. We looked at types of VMs, system VM, process VM, para-virtualization, containers, and we also looked at cloud computing and service models. Okay, what all extra material do we need to refer to? Do we need to know OS before coming to these topics? So I think I had a slide on this. Let me quickly jump to that. Yeah, so I think this was asked on the forum and it's a good template for all of you, so I picked it up. So this is someone saying that I'm currently in my BTech, but this is a postgrad course. Can I do this course? So the answer that was given is, if you're fulfilling it, you can fulfilling the prerequisites. The prerequisites that are listed are fundamentals of comp arc or computer organization, OS, HPC, ML and DL, right? These are the official prerequisites listed, but even if you miss some of these, you can refer to other resources and get fundamental understanding, is what was the answer. So I would kind of emphasize on the same thing. For instance, let's say you've done CompArc, some course on computer organization or architecture, but you have no idea about OS. So what you can do is you don't need to do an entire OS course, because that will take its own time. You can look for a summary of OS or an OS primer, right? A lot of universities would have slide handouts which kind of cover an entire subject in 40 or 50 slides. That will give you a reasonable understanding of that subject, right? So you can do the same thing for whatever prerequisite you are lacking, but broadly, this is what you're expected to know before starting the course. And all of these at an undergrad level should be enough. If you did an undergrad course on organization, OS, some course on machine learning or deep learning, and a little bit of HPC. HPC is not even needed in too much detail. That should be enough to take this course. And even if you haven't, you can always catch up, right? So that's the answer to that. Extra material that you need to refer to will depend on you, right? Like I said, if you don't know a particular subject, you might need to spend more time reading up that particular subject. If you have a reasonable understanding of all of these, then primarily the slides and the lectures with the links in them should be enough. Okay, let's move back to the recap that I was starting. Let's take a time check. So we are at 8 right now, and I think we are at a logical point where we can take a break. So let's see what I have left. So I have a good bit of recap and then a few questions. Okay, let's go through the questions and take a break in a couple of minutes, right? So these are questions that your peers have asked on the Google group. So I've picked up a few of them that are relevant to the week 1's questions. If there are some that have been left out, I will pick them up in the following weeks, right? That's fine. So this is one. This one also I think we already spoke about. Slides will be shared and will be available for download on the NPTEL site itself. So don't worry about slides. Let's see what's the other one. What is a proper definition for an epoch, right? Okay, so we haven't gone through a recap of this, but hopefully you watched the lecture, so you heard of the term epoch. So what is an epoch? The answer that was given was a machine learning algorithm learns the pattern when it sees a collection of data. This cannot be done in a single go, so it has to go through the same collection of data again and again, multiple times. One epoch is defined as the process of seeing all the data once by an algorithm. How many times the same data is seen again and again, that is the number of epochs. So again, this terminology is used. Let's see if I can get a pen. Yeah. So this epoch is used in training broadly. So training is an iterative process, like this answer says, right? So talking about training is the process by which a model or an algorithm learns some pattern from data. So to learn something, the nature of these algorithms is that they are iterative, right? You might have heard of gradient descent, for instance. If you haven't, after today's lecture, go look up STD or stochastic gradient descent. You will understand why it is iterative. So one epoch is basically the algorithm seeing all the data one time. Let's say your data set has 1000 elements, right? 1k elements. So now these 1k elements may be read in batches or groups of, let's say, 16 by the algorithm, and each time the model does some operations on these 16 inputs, and then it comes to read the next set of 16 inputs. So finally there will come a point when the algorithm has seen or has processed all of these inputs. That is called one epoch. But that is not the end of training, because like I said, an algorithm, machine learning training algorithm is usually iterative. So it takes multiple passes through the data before it kind of stabilizes, or before it has learned whatever it needs to learn. So one epoch is just the algorithm or the model seeing the entire data set once, right? And if I need to do that, let's say 100 times, then I would say my training takes 100 epochs for a certain accuracy. So again, we'll go into some of these things in detail in the next few sessions, so you don't need to worry if you don't understand it too well right now. Okay, so this was the set of questions I had. So after this I have a few assignment like questions, so we can go through that as well as a quick recap, since we're already at 1 hour. Once we get back from the break, we'll spend maybe 15 minutes on the recap and move to the questions. So let's see if we have any other questions. Will we be getting the PDF? No, you don't need to take notes. Like I said, you will get access to the full PDF, the recording, everything. So you don't need to worry at all. You will get that. It might take 3-4 days since this is the first time. Okay, so with that, we are at 8:03 right now. So we'll take a break. We'll take a 5-minute break. You want the summary slide? Which is it? This one you're looking for? Great. Okay, I will leave you at this slide. You can stay on the call. I will be here too. You can take a break for 5 minutes and we'll resume at 8:08. Okay. See you then. Okay, I'm back. Hope you guys got a short break, and let's continue. So we'll do a quick recap. Usually I do a 30-minute recap, but I don't think we have the time today. So I'll try to kind of quickly skim through these slides. Again, these are a subset of the overall slides that are used in your course. And again, I will, since we have a diverse audience, I will mention some terms that might be more useful to certain people than others. Feel free to look up those terms if they interest you, or if you feel they're too advanced, you can also leave them, right? There are some things that are optional, but because we have a diverse set of people, I will try to get into those things as well. So here is one of the motivating slides for compute, right? So if you remember a very summary view of AI, you can think of AI as a convergence of three things, right? One is data, one is the algorithms or the models, the other is the compute, right? It is the convergence of all of these that enable large scale massive AI. So why is compute so necessary for AI? This figure is kind of self-explanatory. So on the x-axis is the top 5 error, which is an accuracy metric. So if you don't understand some of these metrics too well, try to ask yourself one fundamental question, right? Is lower better on this metric, or is higher better on this metric? For instance, if I tell you speed, right? You always know that if you're using speed to compare two things, faster should be better. If I tell you error, then you must intuitively think that lower is better, right? That will help you interpret these plots better. So on the y-axis, also notice the scale. Sometimes there are log scales and sometimes there are linear scales. On the y-axis, we have number of operations in gigaops. So this is broadly denoting the computation or the compute associated with every model, and these points are individual models. So if you look at any one particular model, this is how you interpret this point, right? Efficient net B0 has this many number of gigaops, which is between 0.3 and 0.5, and it has a top 5 error of 6.5%. Now if you broadly look at the trend here, you will see that the models with lower top 5 error, basically the better models in terms of accuracy, all have a higher number of operations, right? So the takeaway from this plot is that the compute keeps on increasing. Why does it keep on increasing? You might have certain models that are smaller, but if they have a larger top 5 error, then they might not be preferred in a lot of places, right? So the ones with better accuracy all demand a lot more compute. So this is the takeaway from this plot. So anytime you see a plot, this is kind of a framework I'm giving for you. Whenever you see a plot, it might be a bit complicated. So try to ask yourself these questions. What are the x and y axis? What do they indicate? And things like that. You shared a jam file with the meeting. I don't need it. I'm going to primarily use the slide itself as a whiteboard, because later I'll be sharing the PDF of the slides. So it will be self-contained. Any annotations, any diagrams that I have will be captured as part of the slides. Okay, that's about this. But for some people who are kind of looking at a very advanced view of compute, you might also think about the memory of each model, right? Now I'm telling you that this model has this many number of giga operations. You might think, what about the memory, right? There is another metric called arithmetic intensity, which looks at that, which talks about operations per byte. It's compute per memory, and which goes into a lot more beyond primarily compute. Because if you are aware of compute and memory trends today, memory is kind of more the blocker rather than compute, because compute keeps increasing whereas memory has hit a wall, right? So look at arithmetic intensity for people who are more interested in this, but for others this much is good enough. Then this one is also a quick recap of your memory hierarchy, which you would have definitely seen if you did a computer architecture course or even an OS course. So again, this diagram has multiple arrows. So notice the arrows. Going downwards you have larger capacity, but going upwards you have higher performance, right? So a register file is the smallest in terms of capacity, but look at the latency, right? It is sub nanosecond. So it gives you the highest performance. And going downwards, you will see that as you go further and further down, for instance, if you go to main memory, although it has, you can store many GBs in your main memory or DRAM, it takes hundreds of nanoseconds, whereas this is sub nanosecond, right? And again, if you're curious, you might wonder, why is this so? So what really enables this? And that is more a difference in the hardware, right? You might have heard of different types of RAM, for instance SRAM and DRAM. You might have also heard of newer memory technologies that are coming in today, things like NVRAM, which don't fall into this traditional modern memory hierarchy, but they are also more and more relevant today. So you can look at some of those things, right? Going beyond this is, why are certain things faster but smaller? For instance, why can't I have a register file that's as big as my DRAM? And if you go into some of those hardware details, you will understand that it is not one axis, right? There's always a space of trade-offs. For instance, you might have power, right? You might have space. If I put a lot of one type of very expensive memory technology, for instance registers, then the cost of my chip might go up by a lot, right? That's also something I need to think about. Whereas, and similarly, if I put more of something else, I might be losing the space that I have on chip. So think of all these dimensions when you evaluate these technologies, not just which is faster, which is slower. What is the difference in these memory technologies? What happens if I put more of one thing? What happens to space? What happens to cost? What happens to power? That will help you truly appreciate this as at a system design level, not just in understanding what this is, but why this is. Then moving on. So any questions or any thoughts or comments so far? Feel free to pitch in as I kind of go through the slides. Answered your question, good, glad to hear that. So one different type of compute that I wanted to highlight in this live session is a wafer scale engine. Again, I'm not sure how many of you have learned something about maybe solid state devices or some semiconductor background, right? Fabrication and lithography and things like that. So here's what is a wafer and here is a chip. So typically you have a wafer from which a lot of chips are kind of harvested or yielded, and you might you might see articles where companies talk about getting a low yield and talking about production delays because of this low yield and so on, right? So typically a chip is what is a part of a wafer. Wafer scale is, as far as I know, just Cerebras. It's a very groundbreaking thing that they are the first ones to do, and because of that head start that they have, they remain the only ones to do that so far. But there might be others joining the fray soon. As of what I know today, they are the only ones. So this is it a proprietary idea? Again, I'm sure they might have a patent or they might not. You can check that. If they have a patent, then other companies who come up with something who use exactly that would probably have to pay royalty to them, but I'm not really sure about how proprietary it is or what elements are proprietary. If you're curious, you can go look that up. And they are the largest ML accelerator chip as of now. So they have 40 GB of on-chip memory and 20 petabytes per second of memory bandwidth. So this is to give you an idea of the size relative to the largest GPU. So this is the size scaled to this largest GPU. So the largest GPU is this small when compared to the wafer scale engine. So that's how big the Cerebras wafer scale compute is. And since I think you guys didn't have access to the slides, you probably did not see this blog. So if you're interested in kind of the evolution of hardware and architecture, then this is definitely something groundbreaking, and this blog is something you should read. You will definitely understand a lot more about deep learning, about architecture, and all of those things. What is a stream processor? Again, it's a part of a GPU. So in a GPU you have SMs, right? And then within that you have what is called SPs, streaming processors. So that's that. But I think most of you don't have a very most of you are probably very new to GPU architecture as such. So for next week I'll probably have a 5-minute overview of GPU architecture also. That will kind of help you understand a lot more of these questions, right? Because we don't have the time to go into that today, so we'll do it next week. But that will help you understand all of this terminology, and it will help you be clear about these concepts. So this is about the wafer scale engine, which again is a very different type of compute altogether, right? So typically we talk about CPU, GPU, FPGA and ASICs, but wafers as compute is probably explain about VRAM, okay? Where in the week 1 was VRAM mentioned, just so that I get some context for why you're asking that. Okay, you can take your time to answer that. In the meantime, so these interested in architecture, okay, so I will try to do that depending on how much time we have and how much content we have, but I will note down your question for sure. Okay, so so this again is a graph that shows you the performance density versus time of different accelerators, and here again we won't go into too much detail, but just notice that some of these are marked as int8. The green dots and the lines are all giving you int8 performance density, whereas the yellow ones are giving you FP32. So if you look at a given machine, the RTX 2080 for instance, the performance density is here for FP32 and here for int8. So this is something that is a bit nuanced, right? When a lot of companies report performance of their platform, as a systems person you must always ask, is that int8 or is that FP, right? Because that makes a lot of difference. And again, if you notice, the scale is log here, so this point and this point are very, very different. So a lot of platforms report int8 capacity, int8 flops or tops, not flops really, tops, right? And that might not actually be what you get in real life, because you are doing floating point, right? So that's something you should be aware of. And in case you're not very clear on what these things are, again drop a message on chat. If you don't understand what is FP16, FP32, int8, we can do a brief overview of that too. But you can always look that up. You will find standard articles explaining to you what are these data formats. Okay, that's also something you would like to know. Okay, we can do that in the next week. Let me make a note of that. Okay, moving on. Right, so this is what I was talking about. Broadly, whenever we talk about compute, we talk about CPU, GPU, FPGA and VPU, or more generically an ASIC, right? And there are a lot of ASICs today. There are things like VPU, NPU, basically substitute the V with any X, right? There are that many ASICs available today. But what you have to think about these, if you're interested in an architecture perspective, right? For instance, if you think of deep learning as a workload, and if you think of a workload and then you think about what type of compute is most suitable for this, you can come up with different answers, right? For instance, if you want to be very specific to a certain kind of workload, you can design an ASIC that is meant to accelerate exactly that kind of workload. And that's where this last element, a general, like an ASIC, comes into play, right? Whereas if you want to be as generic as possible, you want to support a broad and wide variety of workloads, you stick to a CPU, right? This is one axis along which you evaluate these. So on the rightmost, as you go towards the right, as you go towards your right, your efficiency increases, but your flexibility decreases, right? These are not flexible enough to support a wide variety of workloads, but they are really good at what they're designed to do. But again, like I said, if you're really interested in the architecture side of things, look at the other aspects. Look at power, look at compute, look at space, look at all of these things, right? Then think of which one is better than the other, because this trade-off space that you have is not one dimensional. It is definitely multi-dimensional, and as you think more about these things, you will kind of realize it. For instance, if you compare the power of a GPU and the power of a VPU, you will see something dramatically different, right? You will see ASICs that are under 1 watt, you will see GPUs that take around 300-400 watts of power. Slide is not clearly visible. You're probably looking at it on a tinier screen, but as long as you can see 4 boxes with CPU, GPU, FPGA, VPU, that should be good enough for what I'm explaining about. Yeah, at this point I cannot do anything more than that, and you will later on get access to the slides where you can zoom in and look at if need be. Okay, we have a question. GPU does int8 execution but produce floating point output. No, that's not what I was talking about. So depending on your workload, you can choose what precision and what mode you want to execute it in, right? Typically for inference, people also do integer execution, right, where int8 is a supported format. Some people might also do floating point. For instance, FP16 is a typically used floating point precision for inference. For training, people typically do FP32. So that's what I was talking about, and I was just talking about the fact that these different precisions also directly contribute to how much performance you get, right, in terms of operations. Can you define what? Say that again. Anyway, moving on. This is again, I picked out across your wide variety of slides. I have picked out some concepts that I think are fundamental and that will help you appreciate a lot more concepts, right? So it might not be every single slide that you see, but it's a very small set of slides. So the other thing that should you concentrate on the images more? If you're asking about the slide content, I think broadly you would concentrate on the takeaways from each slide, right? And if there's something that you probably haven't seen before, for instance, this task parallelism versus data parallelism, I don't think you would have seen it as an undergrad student. So that's kind of why I'm highlighting it. Not necessarily that every slide with an image is more important than slides with text, nothing like that. Any prerequisite for this course? Again, there is a slide on this, so please look that up once you have access to the slides. int8 model will run much faster during inference. Typically, yes. On I think all kinds of accelerators, int8 will be much faster than floating point. Okay, what is parallelism? Okay, so parallelism, okay, people are still joining. Please try to join around 7 o'clock. 1 or 2 minutes later is fine, but if you join in the middle of the session, I end up having to repeat a lot of things that I've previously covered, right? So please avoid doing that from the next time. Anyway, so what is parallelism? Again, broadly, there is a difference between concurrency and parallelism, right? Parallelism means that two things are running simultaneously. Now, there are different ways in which you can achieve parallelism, and again, that's why I've kind of put in this prompt for you to think about this. Parallelism in software versus parallelism in hardware. What are features or knobs that the hardware gives you to have parallelism? One simple example is that there are multiple CPU cores, right? So each of those can perform something in parallel. right? That is a mechanism that the hardware gives you. Similarly, you might have mechanisms to get parallelism out of software, two of which we are looking at today, but there are more, right? So broadly, you need to kind of build up this hierarchy in your mind that will help you appreciate a lot of these isolated concepts to form a very coherent understanding of parallelism. Task means thread. So again, we are sticking to, these are all different abstractions, right? So when we talk about tasks, we are talking at an application level. So I think I have a slide on that. Maybe let's just quickly skip to that. So here is a set of abstractions that will help you appreciate these terms and understand them better, right? For instance, when we talk about compute at a very low level, at the ISA, the instruction set architecture, or the hardware abstraction layer, we refer to them as processor cores. But when you program them as a user, you talk about, as a programmer or as a user, you talk about processes and threads. Now all of these are kind of references to compute, but they are at different abstraction levels, right? So similarly, when I talk about task, it can map to processes or it can map to threads. It is one level higher than that, right? That's what I'm talking about. So let's cover the rest of this, because this is a very general thing that will help you throughout, and it's not really from your course slides, it's something outside. So I will periodically add in things like this that I think will help you gain an overall better understanding, right? And you can refer to them offline as well. So again, if you talk about memory, right, if you look at your RAM, if you've ever seen that chip that you put in, right, that is the physical memory. Now at a lower level of abstraction, you might just talk about this as physical memory. At a slightly higher abstraction level, you might talk about it as virtual memory. For those of you who have studied things like paging, you might know that there are different virtual memory mechanisms available. Now as a programmer, you will talk about pages or you will talk about address space for a program. All of these are still references to memory, but they are abstractions at different level. CUDA WMA, I am not really sure. I will have to look that up. Let me do that and get back to you. I'm not really very sure about what CUDA WMA is. Okay, similarly, storage could be blocks on the hard disk, but you might access them as files, right? And there is a whole other list that you can go through here, but you get the broad idea, right? These are all different abstractions of different abstractions and different ways of referring to the same thing. So similarly, here we are talking about a task, right? And we have some data associated with this task. Now there are two ways in which you can parallelize this. So here what we do, we have one single task, right? Let's say that is to maybe, so I wanted you guys to come up with examples to this, but I don't think we have the time. So I will give you some example and then you can think about more, right? Let's say I wanted to maybe sum up all of these elements, right? Now what I can do is split up all the data I have into disjoint sets. Let's say all of these tasks are basically doing a sum operation, and I split up the data that I have into this many groups, and each of this task performs the sum for some elements. Okay, that sounds a bit complicated. Let's say I have elements 1 to 10 going here, I have elements 11 to whatever, 19 going here, 20 going here, and so on, right? So each of this block basically performs sum, and that is replicated this many times, right? So what you're doing here is you're taking the data that you have and you're splitting it, whereas the task that you have remains the same. So essentially you're kind of gaining parallelism by splitting the data, right? And let's say all of these calculate individual sums across these 10 elements. You will have an aggregation that finally takes in these values and does a final sum on them, right? Something like that. So this is a very simple example of data parallelism. Here in task parallelism, on the other hand, you have some data and you divide it, or you don't split it, but you give it to multiple tasks. For instance, let's say I again have the same 100 set of elements, right? Now I want to find sum of the 100 elements, I want to find average or maybe some other metric, right? I want to find median of the 100 elements, I want to find the mode of the 100 elements, right? So let's say I write 3 tasks to do each of these 3 things. Now I could give all of this data to all these 3 tasks, right? And all of them would work in parallel, and then I would get the resulting data. And again, I could have an aggregation here somewhere, right? So this is an example of task parallelism, where rather than splitting up the data, you're splitting up the task, right? And because of that, you gain a form of parallelism. So this would, again, which one you use will depend on the problem that you have. Looking at the problem, you can figure out which is best suited for this application. For instance, in deep learning, data parallelism is a lot more common, where if you have a data set of 100 elements, you could copy the model onto, let's say, 5 GPUs, and you split the data into 5 parts, right? And you can use it, you can use data parallelism. We will see a little bit of that in the later classes, so we won't go too much into detail on this. And this was something I wanted to discuss, but I think we are kind of, let's see how much I have left on the recap side. Okay, so I will leave you with this question: how are GPUs for the data center different from those on the edge? Think about that. So you have some level of diagrams and details that are given to you through the slides, and look through that and see if you have an answer to this. If so, I will ask a few questions like this to kind of enable you to think on your own about these. And if you find the answer to these, or you have some points on this, feel free to bring it up in the next class. Okay, we have a few questions. Energy, yeah, energy or power, right, is definitely one differentiator between this. You can also think more about what differentiates them and tell me in the next session. Which parallelism is used in edge, grid and fog cloud computing? Again, that's a very, very general question. It would depend a lot upon the workload and what kind of resources you have, right? You could use either of them depending on that. In the slide regarding ASIC, there was a graph of performance density versus here. That graph, performance density of GPU in D8 is having again, I think we'll go through this a little more in detail in the next class if you have questions. Yeah, let's do that. Accurate, less accurate. Okay, interesting. Think about how the GPU would accomplish that, right? What would you do in terms of hardware design? Less hardware. Okay, fair enough. For instance, if you have int versus FP, you can kind of reduce your hardware complexity, and that in a way is accurate, less accurate than something that gives you full FP32. Okay, I am going to skip some of these slides. So again, how many people, I think someone wanted to know about DJX, so I'll probably include this in the next week's slides, and we will go through tensor cores also. This let's cover today. So what is an operating system? It's basically a bunch of software, but it's not just any software, right? It is the most privileged software in a computer. What does that mean? The OS can do special things like writing to a disk, talking over the network, control memory and CPU usage. So it's also a system resource manager, right? So why do you need something that's more privileged than other programs or processes is the question, right? Again, think about that. I don't know if we have a slide here, but that was also already covered in the lecture, so it shouldn't be too difficult, right? If think about a scenario without an OS, what are the things that malicious programs could do to the system? That would kind of answer your question. Is OS the only system software? So you have certain other things. Again, for instance, drivers and things like that, right? And depending on the operating system, for instance, Windows has this concept of user mode drivers and kernel mode drivers, and the user mode drivers are not really in the kernel space or the privileged space. So broadly, to answer that, OS is not the only system software. There are some things that also fall into system software that might not fit exactly into what an OS is. Okay, VMs. Are there performance benefits in using one kind of parallelism over the other, or would it be use case specific? So again, in deep learning specifically, there are three kinds of parallelisms that are spoken about, right? Data parallelism, model parallelism, and pipeline parallelism. Again, we will look through some of these in the later lectures, but broadly, data parallelism is used when your model can fit into the GPU and you can kind of run it, but you want to accelerate it, right? So what you do is you split up the data. But model parallelism, on the other hand, is often used when you can't fit the model into a single GPU. So what you can do is partition the model into different GPUs. So this is a kind of specialized parallelism. It's a specialized realization of task parallelism for deep learning. And again, you have further improvements over this in things like pipeline parallelism. So it would depend on the hardware that you have, the resources that that hardware has, and also the application. So it is a bit of a generic, it's not really a generic call, I would say. It depends on what hardware you have and what problem you have. Linker, loader, assembler. Yeah, you have a bunch of things. Again, how many of these fit into broadly the kernel set of things, how many of these are outside those would depend. Okay, we will skip through VMs as well. I think you would have had a reasonable idea. And since next week also covers things like containers and Kubernetes, I think I'll move some of these into the next week and we can look at that. And this we will come back to. This also we will come back to in one of the questions, right? So we already did the discussion forum part of it. So let's move to the problem solving. These are again quite simple because the first week did not have very involved math or compute or something like that. So it's broadly recall and understanding based questions. So I will read out a question, they will have 4 options, and then I'll give you a minute to kind of tell me what's the answer, and then we can discuss it. So that's how we'll do this. I think we have 7 or 8 questions and they should help you in solving the week 1's assignment. So let's get started with that since we have around 18 minutes left. Okay, FPGA based accelerators have low power acceleration, high reconfigurability, low latency, all of the above. Answers, if you have an answer, please put an option number in the chat box. For instance, if you think it's C, put C. If you think it's B, put B. As simple as that. And don't hesitate, this is not a test. I'm not going to be counting the people who get the wrong answer or the right answer. Why I ask for interaction is it'll help me explain better. For instance, if most of you get a particular question right, then I know that you've kind of understood it. But if you don't, then I know where I need to focus, right? Okay, many people think it's D, someone thinks it's C, A, B. High configurability means generalization. That's kind of it's not really completely generalization, but it's more along the flexibility or how much you have room to adapt to different workloads. So it's probably very close to generalization. can adapt to various hardware, not really hardware but workloads. I'll wait a few more seconds. Okay, let's take a look at the answer. It is actually all of the above: low power acceleration, high reconfigurability, low latency. Now again, I know we didn't go into a lot of detail on the FPGA architecture side. So this is, I think this also might not be visible, especially for people on a smaller screen. So this was kind of, I think, the architecture diagram shown to you, but broadly I think most of you have uh, have clarity that it is a low power thing and it is a low latency thing. So the low latency, so again, this was something I was planning to ask you guys, but we don't have the time, so I'll give you a brief overview on that. So it is relatively low power when you compare it to a GPU, and again you can think about why that is, right? And it is low latency too, and that comes again from an architectural design, right? A lot of memory is available on chip, whereas for GPUs, again the memory design is very different, right? So the low latency part mostly comes from the memory aspects of it, and the reconfigurability comes from being able to adapt to a variety of workloads and a variety of precisions. For instance, on FPGAs, you can actually do any bit computation. For instance, it doesn't have to be int 8. You can do 6-bit, you can do 3-bit, you can do 4-bit, right? It has that kind of flexibility or reconfigurability. Again, this is because of architecturally how it is defined. So if you guys are interested, again, this is not fully in the scope of the course, but if you guys are interested in knowing how an FPGA is different from a GPU, we can have a slide on that next week, which will help you understand these elements better. So if you are interested, again, leave a message on chat and I will cover that in the next week. But for today, this is why it's the answer. When GPU can be preferred over FPGA? Yeah, that's exactly one of the questions that I have asked, right? So that's something you have to think about. And again, like I said, it's a multi-dimensional space. For instance, how much power can you afford, or how much memory do you need for your workload? So once we go through, so the continuum from application to system software to architecture to hardware is very it has a lot of, yeah, the name itself expands to gate array, field programmable gate array. So yes, we can cover a little bit of the architecture differences between FPGA, CPU and GPU. That would help you. Yeah, cost is another definitely very important thing, especially if you're looking for practically deploying these things and buying hardware and all of that. So it is a continuum. I meant that features from architecture and hardware enable certain things about the workloads, and certain things about the workloads necessitate certain features in the hardware, right? So we can go over that a little bit later too. Bit level, is that a question or was that a comment on something? I'm not very sure, but let's move on in the interest of time. Okay, here's another question. Energy consumption for a 32-bit floating multiplication is dash. So this is again a recall question, so there's not much to it. You can't calculate it. If you remember it, you know the answer. So we have one answer, C. Anyone else? C. Okay, we will look at the answer. It is C, 3.7. It is based on this graph that you had. But beyond this question and this answer, I would like you to look deeper at this graph and think about what takes energy, right? Is it computation? How does it differ between between different operations, between different data formats. Is it universal? Why should we memorize? So again, some of these questions will test you on basic recall and understanding. They might not be super important from your understanding of concepts, but just because that's easier to put it in an MCQ format, the course instructor or NPTEL might choose to do it that way, right? So if your aim is to get good grades in the NPTEL course, then some of these things you will have to remember. If your aim is to just understand concepts and getting a few questions wrong is okay, then you don't need to remember, right? That's the answer. But more broadly, I would like you to look at which operations take more energy and how that changes with data formats and things like that, right? Is there a way to calculate model power consumption? Yes, if you have power sensors on your hardware, you can do that. If not, you can also use a wall socket power meter that can then measure the consumption from the wall socket. That will not just be your model power, but it will be the power consumed by the entire system. If you want the incremental power, that is the power consumed only for the model part, how this is typically done is there is one measurement done with no workload running, where only the system is running, and you take power measurements or energy measurements, and then you take measurements with the model running, and then you can subtract this system power or system energy from your total energy. That will give you the model's energy. Hope that answers your question. Final paper will be in MCQ format. Yes. 640 picojoules for DRAM. Is this for data writing or retrieval? I don't remember. I think you should go back and look at the slide. That should answer your question. If not, ask me. Libraries for energy consumption in Python. I am not very sure about that. So if you have a power sensor on board, then typically you will have a way to poll that power sensor, and the hardware vendor will give you some library as well. For instance, if you look at edge devices from NVIDIA, they have a library called TegraStats, right, which reports power. So you can just poll that or call that in your Python file. So it would depend on what kind of sensors and what kind of power monitoring system you're using to get this data. Okay, let's move to the next one. How many streaming processors are present in a V100 GPU? In a V100 GPU is SM. Okay, that's a slightly different question. Again, this is a purely recall question, so if you remember it, you know, otherwise you don't. 64, we have one answer. 16, 32. Okay. 32, I see. Okay, let's look at the answer. It is 64. So again, this is taken from the slides. So you have 5120 stream processors, but this is asked about a single SM, right, or a streaming multiprocessor. So in a single SM, there are 64 streaming processors, or in this slide you see it reported as 64 functional units per core. And again, you can take a look at this architecture white paper. You will get a broad idea of what these things are. But I'll anyway do a quick overview of GPU architecture in the next class. Okay, again, from a course standpoint, do I need a GPU powered? Not really. You can understand the concepts even if you don't have access to a GPU. If you need to run some things, I think the course instructors will give you access to some sort of cloud platform where you can do that, so you don't need to worry about that. Which of the following is not an FPGA accelerator? Again, if you remember all the accelerators that were mentioned on the graph, you would know. We have one answer saying A. Anyone else? WSC. Maple. Okay, we have all answers. So the answer is B, Cerebrus. Like I said, wafer scale engine does not fall into any of the typical categories, neither CPU, GPU, FPGA or ASIC, right? So that is definitely not an FPGA accelerator. In case you don't remember anything about the other three, there's still a way to answer this question. Otherwise, if you remember that figure that was used in the slides, then all of these are listed as FPGA accelerators. Okay, next question. Which of the following is not an ASIC accelerator? Iris, Vitis, MATLAB, Maple. So DLA, from the name, it should be a deep learning accelerator. Iris, I think, was an FPGA accelerator. So probably the answer is Iris, but I'll have to get back to you on that. I'm not very sure about, yeah, from this question, it is Maple. It is Iris. Let me see the next question. Have an RTX 4050, doesn't have power sensors. You can have an external power monitor, right? You can purchase one of those that you plug in between the wall socket and the plug. That will measure power externally, and depending on what kind of power monitor you pick, it will have a way of recording things. Some of these, for instance, come with SD cards and they will record data every second or every 5 seconds or something like that, and then you can get that data off an SD card. Okay, so which of the following is not an ASIC? You can figure that out. I think look up all four and then you will figure it out. To access services of the operating system, the interface is provided by dash. Any answers to this? API, okay. System calls. Okay, everyone seems to know this. Week 1 is based for IoT, not really. It's intended to give you an overview of the various things that you need to understand this course. Unable to access Jamboard. I don't know why you need a Jamboard. I'm sharing screen here and my slides are self-contained, so this should be enough. So the answer is system calls, and this I think was not in your slides, but it's a useful diagram to have in your mind, right? So whenever the application needs certain privileged functions, privileged operations, it asks the operating system, can you do this for me? And that is through a system call interface. So there is this notion of a user mode and a kernel mode. The kernel mode is the privileged mode. So for instance, if you have a file open that you write in whatever API that you use, Python or whatever, ultimately it will go into a system call, which also coincidentally happens to be called open, and that the OS will shift to kernel mode and implement this functionality for you and return back control to the user application. So it's basically like asking a more privileged person to do whatever you need, right? That's about it. Which of the following is not a characteristic feature of process VM? Okay, we have answers. D. D, runs in privileged mode. B, virtualizes the API. C, D. Okay. So the answer is D, runs in privileged mode. So here's a snippet about the process VM, right? So it virtualizes the API. Again, try to understand what each of these interfaces represent, right? The API, and so on. And it does perform binary translation. It just runs in non-privileged mode. So this is the contradiction that you have. So D is not a characteristic of process VM. We'll take the next question now. AWS EC2 is an example of dash. And in the meantime, I'll look at the question on chat. Pre-training models, what should be preferred in the context of overall cost? Cloud or local system? See, that depends on what you call cost, right? Are you talking about cost as in your operational cost and your capital cost, right? With the cloud, there is no capital cost. Whereas if you want a local GPU machine, you will have to invest some amount on it. But with respect to an operational cost, with an edge device, you might probably have an energy cost associated. Same for a GPU workstation. With the cloud, you will have to pay for services that you use. So again, it's this trade-off of how much compute you need, how much cost you are willing to pay. Again, has to be evaluated on a case-by-case basis. So we have answers to this saying IaaS, and that's right. So this is based on this pyramid that you see here, and it's fairly self-explanatory, right? So depending on at which level you offer something as a service, the apps would. So if I ask you about AWS, you would think about what is handled, what level of control the users get, and what level is already kind of handled by the platform. So this is kind of self-explanatory. I will skip over it. And cloud services have a dash relationship with their customers. Many to many, okay. Many to many. One to many, many to many. Okay, let's look at the answer. It is one to many. So if you think of a cloud service, it can have multiple customers, right? So it is kind of a one to many. But if you think of multi-cloud as an example for this, then it could also be many to many. So I kind of get why some people think that it's a many to many thing, but the official answer key that's given by NPTEL is one to many for this. So they are probably talking about one particular provider, cloud provider, and how many customers they can have. So from that perspective, it would be one to many. Moving to the last question, one example of past is dash. Gmail, Google Docs, okay, Google App Engine. Again, if you look at the pyramid, it's kind of it explains things, right? So yeah, platform as a service is Google App Engine. So I won't go into too much detail on this. We are a minute over time, so I will wrap up here. So that's all I had for today. I will cover some of the recap slides that we didn't get time for today in the next week. And I will spend a lot more time on problems, right? So we'll typically have 8 to 10 questions every week, but we will go into a little more detail, see if some of you understand things, don't understand things, and so on. So I'll stay on the call for a couple more minutes. If you have any doubts or any questions, put it on the chat box and I'll pick it up for the next week. Repeat question 6. Right, this is a process VM, right? Thank you. If you don't have any questions, we are already 2 minutes over, so feel free to leave the call. If you recording will be shared, and if you have any feedback on the session structure, right? You liked it, you want it to be the same way, or you think it should be something else, feel free to share that too. Okay, 5th question. System calls. Right, so this is like the application asking the operating system to do something for it, right? For Sunday live session, there will be another. Yes, there are 2 team members. So one of them will be handling the Sunday, I will be handling the Monday sessions. Every week that will be the same. This PDF, you will get it. It will be shared with you. You don't need to worry. In the class, it was explained as 3.1 picojoules. I don't remember the number. I can double check that for you. So system calls are broadly when the application makes a call, asks the OS to do something for it, right? So you can look up why is this needed, because the application does not have the privilege to do certain operations. Yeah, thank you so much. Glad you liked it. So things like Please put light on tensor cores. Sure, I can do that. I planned to discuss it today but ran out of time. So yeah, I think we will do that. I will also include system calls in the next session, so we will spend a good amount of time on it. Since we won't have 30-40 minutes of the intro, we can quickly cover topics. I will end it here because I know most people have already had enough of 2 hours, right? So let's stop here and we'll continue next week. And thank you so much for joining in and keeping it interactive. Hope you benefited from this session. Thank you. See you next week.